Thank you. Welcome back, or welcome to DefCamp. And today's session is, as you can see, hacking MySQL for big data. I'm not sure. Okay. So as you can see, the title of this session is Hacking MySQL for Big Data. And for those who are interested in what this speech is about, it's not about how to breach or break into MySQL databases or into databases altogether, but rather how to make your databases perform, make MySQL perform better on big data. So for those who are interested in, for those who find yourself asking why you should listen to me, as already mentioned, I have authored a book conveniently also titled Hacking MySQL, Breaking, Optimizing, and Securing MySQL for Your Use Case. I'm also the founder of BreachDirectory.com, which is a data breach search engine. I worked with former MySQL staff at several nines. At Archetype, I work with DB Visualizer, Redgate, and some other companies. I partner with MariaDB to deliver content, and I speak at a lot of conferences, including Percona Live, MariaDB Serverfest, this conference, Build Stuff, and so on and so forth. So let's get into the talk, shall we, right? So in this talk, we're going to go through a bunch of things that you probably find yourself asking if you find yourself working with bigger data sets, whether or not you find yourself working with MariaDB or MySQL. So we're going to start from the basics and answer the question, what is big data in the first place? When and why you should use MySQL when working with those big data sets? What's the role of MySQL for your big data use case? What's the role of MySQL for your specific use case? How it can be used for data breach search engines. Perhaps you're thinking of building one or already running one, I don't know. And also some things you should know. And we're also going to summarize the talk afterwards. So to begin with, we're going to be answering the question, what is big data, right? So by virtue of being here, you're all security people, you're all developers at least. So if I would ask 5 or 10 of you what is big data, I would probably get 5 or 10 somewhat different answers, but also answers that are somewhat related to one another. And most of you would say that big data is something that consists of a lot of rows, a lot of data. That's something that ordinary systems cannot really deal with, or something like that. So we have to sort of define what we're talking about in the first place, because if you ask many people the same question, you get many different answers, so it may be unclear. So in this specific case, what we're considering big data is something that we work with that has hundreds of millions of rows, maybe 100 million, maybe 200 million, maybe a billion, who knows, maybe over a billion, that has a specific use case. That means that you use these rows, this data, to accomplish a specific goal, and also data that's formatted in a specific way. So it's most likely going to be formatted for either relational database management systems in the form of text files, or perhaps SQL files, or maybe JSON files if you're working with NoSQL. So the first probably question you're going to be asking yourself in this case, when and why you should use MySQL to work with big data? Because to forward it back a little bit, turn it back a little bit, you will always find people saying that using MySQL for big data sets is close to impossible. They say that because MySQL by definition is a relational database management system. And by definition, database management systems, relational database management systems, they're based on one principle, that is ACID principles. And somehow people think that even if they optimize the database to the max, these principles somehow are not a fit for their big data use case, but that's not the case. So to begin with, you have to consider that MySQL is not only MySQL. MySQL is MySQL Server, MySQL is Percona Server, it's a different flavor, and it's also MariaDB Server, which means that it has 3 different flavors, and each of those different flavors has something to offer. So for example, Percona Server has this storage engine called XtraDB, which is essentially an enhanced version of the primary storage engine available in MySQL, which is InnoDB. MariaDB has a bunch of other storage engines available to you, including Araya, Sequence, and so on and so on, and you have to choose very carefully. So another thing that you will find when working with MySQL, as I already mentioned, is that it's ACID compliant. I'm going to talk about a little bit more what it means for your specific use case a little later on. But this thing, essentially, what it means is that it keeps your data consistent, even in the case of electricity going out, your internet going down in the middle of the query, and so on and so forth. Also, MySQL is a very big friend for vanilla-based use cases, that is basic use cases, and some use cases that might make a special use case of the ACID property that I just talked about, right? So after you understand that, you have to consider what's the role of your database in the picture as a whole. So all databases, they don't really come with one thing that's called a database, right? They come with a lot of internals, and those internals are sort of outlined here. So we start with the file system. Each database management system comes with data. So you store databases. Those databases have files inside of them, have tables inside of them. And those databases and those tables are essentially represented as files on your disk. Those files also may have index-related files if your table has indexes on them. There's also log files that you have to worry about, because log files are used for your database to go through when you're restoring from backup. Storage engines, when it comes to storage engines, you're most likely going to use InnoDB, because, as I said, it's the primary storage engine available in MySQL, and MariaDB in that case. But there's also other storage engines that you might want to look into. For example, MySAM. Nowadays, it's pretty much obsolete, but back in the day, it was a pretty good storage engine until InnoDB has replaced most of its features. And nowadays, it is also a fit, but for a very specific use case. Since InnoDB does not really store the row count of the rows inside of the table inside of itself, and MySAM does, you can use MySAM to essentially get a count of the exact row count in the table. There's also the parser, the optimizer, and an SQL interface, and these three things are something that your database will necessarily go through when you run any sorts of queries, because queries are going through the parser, which means that they are parsed into smaller parts that are then processed. And once they're processed, they go into the optimizer, which means that your database starts thinking how best to optimize the query, how best to execute the query. And then you have some things called caches and buffers. Let's say returning data from the cache is going to be always faster than returning data from the disk. And you also have to think about how you connect into your database. So there's connection pools and a bunch of connectors that you can use. So connectors, you can use it to connect with Python, you connect with C, you connect with PHP, and so on and so forth. After you understand what your database is about a little bit, it's time to think about your specific use case, right? My specific use case, for example, is a data breach search engine, as I already mentioned. All specific use cases will, at the moment you look at it, you will always have something that concerns your database, right? So this, for example, it's one page, right? But it also tells you lots of things that I'm going to get into in a moment. Right? But before building these things, you have to code them. You have to get into the brains of your database, right? So if you're building data breach search engines, or any search engines for that matter, your queries may not look as complex as you think they might look, you know? For example, this is how some BreachDirectory code looks like. In essence, what you see here is a loop that loops through tables in a database, and in essence acts on user input. Basically, you take one query and you loop through all of the tables in a database and then return results. The reason why it is so fast is because it doesn't take unnecessarily steps. If you, for example, if you visit breachdirectory.com right now and you search for any account right now to determine whether you are at risk or not, you will notice that it returns results in a millisecond. And that's why, and that's the primary reason for that happening, is because the database is properly configured. It's properly configured because MySQL makes it very easy for you to do so. For those using Windows, MySQL makes it even easier for you because its configuration file will be called my.ini instead of my.cnf on Linux, and it will come with a bunch of comments that you can make use of, a bunch of comments from the MySQL team that you can make use of to, in essence, make your databases more performant. But if you're using Linux, this is probably what you're going to see after you open the configuration file. And these things are pretty basic things. They're nothing very complex after you dig into them. Right? So log error, it's obviously the place where your database stores the error log file. This is an error log file that obviously stores all of the errors that are encountered by your database. It's nothing hard to understand, but it must be defined if you want your use case to actually assist you in the process. Next up, we have the storage engine definition. So default storage engine will almost always, without exception, will be defined as InnoDB, because as I said, InnoDB is the ACID compliant storage engine, and during the years it has advanced so much that it became infeasible for the MySQL team to offer anything else to you. And then you have the rest of the options. So you have the file per table option, as you can see here. File per table option, what it does is essentially has to do with the table space of InnoDB. What I'm talking about is InnoDB had a table space file called ibdata1, which is also defined right here. Right, this is another parameter, and this table space file, back in the day, it used to house all data and all indexes and all partitions from InnoDB, and once that file would be deleted, everything in your database would be deleted. So in essence, if you delete that file, you lose everything inside of your database, and there's no going back. But the core premise of the change indicated in the configuration file was the following. Basically, MySQL team understood that the ibdata1 file houses everything, and it is better to split everything into separate chunks with InnoDB file per table, which means that your tables and databases will be stored in separate files. And nowadays, the ibdata1 file has a size definition that is defined here. It can be extended to a maximum value that is defined here, but it will only store metadata from your tables and from your databases. That means that InnoDB ibdata1 file, the table space file, the most important file, it won't get as large and it won't cause you many problems. But aside from that, you have a couple of other important parameters to take care of, the main one being the InnoDB buffer pool size, which you can see here. What this parameter does is essentially defines the amount of operating memory that is available for InnoDB, the main storage engine, to use. In essence, if you have, for example, 32 gigabytes of RAM, you may define this variable to be 24 gigabytes of RAM or something around that area. It is recommended to set this parameter to 60 to 80% of available memory and set the rest of the options, which are defined underneath these options that have to do with the log files, to a quarter of its value. So if this is 16 gigabytes, the log file size and the log buffer size will be 4 gigabytes. The reason why, it's because it's just best practice, and the log files will be scanned through when you restore data. So this will be the best of both worlds for you. Now, flush logger transaction commit is also very important, but you most likely won't need to change it either, because what this does is essentially tells your database that you want it to be an ACID compliant database. It has other options. It has options 0 and 2, and these options essentially trade ACID compliance for more speed. So if that is your goal for any sort of scenario, you might change it, but in most cases, it's not necessary. And that's kind of it. And these options are the main options you will see in a Linux configuration, but you might also see options like InnoDB log waits timeout, which is some miscellaneous options that have to do something with InnoDB. So for example, this specific option, what it does is defines the time in seconds, and InnoDB waits for a row lock before timing out. Row lock means that any case where your rows are locked, basically, whenever your query starts to run faster. Right, so understanding these things, you can look into your use case once again, and you can see what what parts of your use case or what parts of your application have to do with the database. So as I said, my specific use case is a data breach search engine available at breachdirectory.com, and it's essentially, you can see on one page, we have many things that have to do with the database, right? First of all, we have the row counts. These counts obviously come from the database, right? The second thing, we have available choices for the user, so you can search for username, email address, IP address, or whatever. And then obviously you have to insert a search query for your database to process it. And then you might be able to use wildcards, which are essentially allowing you to introduce specific search operators to make your database search for exotic kinds of data. So this is how it works. Essentially, you might also find other types of options that have to do something with your database, for example, returning results. So this obviously has to return results from somewhere, so most likely a database. And you will find that the way you format results also has to do with the database. And so you have to account for everything accordingly. So after you optimized everything, after you got into your use case, you will have to consider a couple of things once again. You will have to look into your database and your specific use case once again. Why I'm mentioning this? The reason why I'm mentioning this is because your database has a lot of things to consider, and you have a lot of things to consider when working with the database. So if anyone has worked with the database, you obviously worked with queries. And what do developers say in regards to queries most of the time? Most of the time they say they're slow, right? So what's the reason behind that? Well, the reason behind that is because all queries come with overhead towards your database. Overhead means a bunch of tasks that your database has to complete before completing the query. If those tasks are not completed, your query will not complete, and then developers say, my query is slow. So in regards to overhead, right? So when we talk about query performance, if anyone has read any books or any articles in regards to query performance, in essence, they all can be sort of summed up in the following way, right? So your database has a bunch of tasks to complete when completing queries. These things are all steps that are taken by your database when completing a single insert query. So in essence, your database has to start, right? It has to check for permissions, open tables, initialize, do other things, update, end, query end, close tables, free items, and clean up, right? And these are all things that your database has to complete when it is working with one query, right? So you have to consider that if you're working with big data sets, you're not working with one query. You're probably not even working with 100 queries or anything like that, right? You may be working with 100 million queries, a billion queries, right? And if you run one query and it completes fast, it doesn't mean anything, right? As in this case, right? Because one insert query might complete fast, right? But if you try to insert 100 million records or a billion records into your database, that means that you take these things that are outlined right here and you times them by 100 million or a billion times. And here you have it. You have to wait 2 weeks instead of 2 seconds for your query to complete. And this is the primary reason why developers say that my queries are slow, because these tasks aren't optimized or they aren't deleted altogether. So to optimize query performance, what you need to do is actually very simple in the most imaginable way possible, right? So what you have to do is take these tasks and either make their execution time, which is displayed here, slower, or eliminate them altogether, which means that this execution time will not even exist anymore, right? So after that happens, your one query completes faster, and after that happens, your 100 million queries will also complete faster. Right, so next logical question will be, how do I do that? Well, if you're working with select-based queries, for example, if you're reading the data from the database, you're most likely looking into indexing. So indexing in MySQL is also sometimes misunderstood because people say that MySQL has all kinds of indexes, covering indexes, composite indexes, clustered indexes, and blah, blah, blah. but also these all indexes are a part of a B-tree index structure. MySQL has two index structures. They have B-tree index structures, and they have R-tree or spatial index structures. Basically, B-tree index structures is everything that is not spatial indexes. Spatial indexes, in essence, they just index geographical data. So if your use case does not necessitate that, you will just probably ignore it. But other indexes you have to consider. You have to consider because each type of index works in a specific way. For example, covering indexes, they cover all the columns necessary for your query to complete. And once that happens, your query is able to read data from the index instead of from the disk, and this is why your query is so slow, query is so fast, right? Composite indexes, they just mean that you have, in essence, an index on multiple columns. Descending indexes store rows in a descending manner. Full text indexes, they may be useful if you're running, for example, wildcard search operations, and have specific bugs in and of themselves. For example, if you run a full text search query that has that runs on a data set that has an eta sign inside of it in all the versions of MySQL, 5.7 if I'm not mistaken, the eta sign will slow the query down to a crawl because there's a bug in MySQL that doesn't let it complete. These things are usually obtained through experience, right? And experience is obtained by doing things and reading the documentation, right? So if you read the documentation and notice that one type of index is not a fit for your specific use case, maybe another is. And if another isn't, maybe the third is, right? So after you do that, you will come up with some sort of a plan how to work with your database. What you see on the screen right now is the way your indexes and your database interact with each other, right? So after you run a query, your database has to consider how best to execute it, because this is what databases do. They consider how fastest to execute the query. What is the fastest way to execute the query? And if you run select queries and if you have indexes on any columns that are affected by the query, your database is most likely going to use an index. Now, what kind of index is in use? Well, this actually heavily depends on a variety of factors. So for example, in this use case, we select two columns, right? So if we have one index that covers both of these columns, that means that it consists of both of these columns of inside of it. It may be a covering index, and in that case, the database may read the rows from the index instead of from the disk, and it may return rows based on 1 millisecond instead of, may return rows after 1 millisecond instead of 1 second, right? And that has an impact. So the things you have to consider are sort of split into two categories, right? So one of it may be more important and the other may be less important a little bit. So first thing, as I already mentioned a couple of times, covering indexes means speed. The covering indexes, they mean speed because, as I already said, when they are in use, your database has to read data from the indexes instead of from the disk, and that's significantly faster. You can also use indexes and partitions, which is something that some people don't consider. They either consider using indexes, either partitions, but you can also use both. They will obviously cost you a lot of disk space, but in return, they will provide you a lot of query speed. You also need to consider what you're indexing. So for the best performance, you may consider indexing the column after the where clause, and you also only need to select the necessary rows, because the more rows you select, so for example, if you do select wildcard from, it's automatically the wrong approach, maybe because if you select column from, your database has automatically to work through less data to return results. And this is why your queries complete faster. The other things you have to consider are related to storage engines and your configuration file. As I already told you, you have data types and character sets that you have to consider, right? So these things are also important, especially if you have a lot of data. So you may be not using text data types. You may be using varchar data types with 40 characters instead of 200 characters. This approach will take less space on the disk, and it may may, in essence, lead to the same results, and you will save disk space. The other thing you have to consider is what columns are indexed, and does indexing even make sense in your specific situation? Because if you have 20 rows, indexing anything, it's not going to make a difference, most likely, right? So when you are considering these things, you are most likely going to use something akin to the explain query or something like that. So the explain query has a couple of outcomes that are visible in the additional column, which are outlined here. There are 4 visible outcomes. So your query has either, you will see either using the index condition, either using a where clause, either using a file sort, either very rarely in very specific scenarios, you may see impossible where. And these things, what they mean is, in essence, using the index condition means that MySQL filters rows by using the index and then uses the table to retrieve the matched rows. In essence, that your index is being used. Using a where clause, for many people, they say that it can have different meanings. Some argue that this information is inconsistent at best, but in this specific case, what it most likely means is that the expression within your where clause, the expression within after the where clause has performed an index seek operation. An impossible where can also be a possibility, but it's often only a possibility if your query doesn't make any sense. In essence, that's your database telling you that your query is nonsense. That happens when you, for example, have 1,000 rows in the table, and then select the row number 1,740,007. Right? So that doesn't make any sense for the database, but it doesn't tell you specifically that directly. So it tells you an impossible where. And what this means is that your query doesn't make any sense, right? And there are many other things you have to consider, but unfortunately, the rest may be on you, or maybe on you and your team if you're working together with a team. But I have good news. Everything that you have heard in this presentation and 100,000 times more is outlined in my book, Hacking MySQL. And if anyone's interested in a copy or maybe a discount for a copy or a complimentary copy for free, feel free to get in touch with me and I will arrange your copy. I unfortunately don't have any copies of the book, any physical copies of the book with me, but I can, if anyone would be interested in reviewing the book, for example, I can hook you up with a free copy, and that's that. So thank you so much for listening. My database search engine can be found at breachdirectory.com. You can reach me at my email that you see on the screen right now. And if you go to my website and then /feedback, you can also leave feedback about how I did in this talk, whether you liked it, whether you didn't like it. And thank you. I hope this speech was informational. I hope it was useful. And I hope you learned something from it. Thank you very much.
Thank you so much, Lukas. It's now time for questions, and we have plenty of time for them. Please keep your hand up. In 3, 2.
Hello. So thanks for the presentation. It was really cool. My question would be, how would you perform a benchmark for such a database on MySQL upgrades when it's very hard to replicate the production state? Like if you have like 100 terabytes of database and you can't replicate that in dev, how would you actually benchmark an upgrade?
Benchmarking these things is actually it's actually more simple than you may think about. So what you do is you have a local instance, maybe a local MariaDB instance or a local MySQL instance, and you use the necessary vanilla tools. For example, I think it is MySQL slab or MariaDB slab that let you emulate certain kinds of queries on certain kinds of data sets. Even if you don't have the data set, you can tell MariaDB slab or MySQL slab to emulate this specific kind of query on this specific kind of result set. So this is how it's done. In essence, you test, and you come up with results. Actually, benchmarking is only one part of it. You also need to use queries like the explain statement in front of your query that will contain a bunch of information that is also useful for your use case. So, but benchmarking, it was most likely be done like that. Yeah. I hope this answered your question.
Cool. Thanks so much. Next question. This is a safe space. If you want to ask your questions. Another one. Okay. Yeah, let's go.
So you mentioned partitions earlier and indexing.
Yeah.
Would you prefer partitions over, let's say, like creating multiple tables for the same data? Like, would you rely on the MySQL partitioning system, or would you prefer custom separate tables for separate, let's say, distinct data that would occasionally be joined together?
There's usually no need to invent something of your own. MySQL has a very great partitioning system. It has a couple of partitioning types you can use, and they usually cover all kinds of use cases. So for particular, if you're using partitions for search engines, there's partitioning by range that you can arrange in such a way that you partition, for example, you have 27 or 28 different partitions, depending on how many letters are in the alphabet. You split this table into 28, 27 different partitions. And then in essence, since these partitions are still treated as one table by your database, no, these partitions will be treated as separate tables internally, but they will show as one table to you. So it will be easier for you to work with them. And can you repeat the first part of your question, because I didn't really understand?
The alternative would have been to create a separate table, like invent a system yourself. That was the question.
As I said, there's no need to invent anything yourself, and usually if you have a lot of rows, a lot of data, it usually depends on how much rows you have, how many rows you have. If you're considering using indexing, you're maybe considering using indexing on something that has 50 million rows or 100 million rows or above. But if you have 1 billion rows or above, you can also consider indexing and partitioning at the same time. It will obviously chew up more disk space, but it will provide you with efficient results. So that's that.
Thank you.
Thank you.
Thank you as well.